Analysis of heat exchangers. So heat exchangers are commonly used in practice, and an engineer often has to select a heat exchanger that will achieve a specified temperature range in a fluid stream of unknown mass flow rate, or to predict the outlet temperatures of the hot and cold fluid streams in a specified heat exchanger. In the upcoming sections, we will discuss two methods used in the analysis of heat exchangers. Of these, the log mean temperature difference, or LMTD, method is best suited for the first task, and the effectiveness NTU, which means the number of transfer units method, for the second task. But first, we present some general considerations. Heat exchangers can be modeled as steady flow devices. As such, the mass flow of each fluid remains constant, and the fluid properties such as temperature and velocity at any outlet or inlet remain the same. Also, the fluid streams experience little or no change in their velocities and elevations. Thus, the kinetic energy and potential energy changes are negligible. The outer surface of heat exchangers is assumed to be perfectly insulated, so there is no heat loss to the surrounding medium, and any heat transfer occurs between the two fluids only. The first law of thermodynamics requires that the rate of heat transfer from the hot fluid be equal to the rate of heat transfer to the cold one. So here in this picture, we have the hot fluid coming in and going out, and the cold fluid coming in and going out. So the cold fluid is heating up, and the hot fluid obviously is cooling down. So we can use the first law. So it's the mass flow rate times the specific heat times the change in temperature difference. The only difference, so the Q's are the same for hot and cold fluid. The difference is obviously in between the flow rates and the specific heats. Typically, the product of the mass flow rate and the specific heat of a fluid is combined into a single quantity. This quantity is called the heat capacity, and it's defined for the hot and cold streams as follows. So we use a capital C with an H, or capital C with a small c. It's the mass flow rate times specific heat. So using that definition, we can rewrite the first law as the following sets of equations. So there are two special types of heat exchangers I want to talk about now. A condenser and a boiler. A condenser changes a gas to a fluid, and a boiler changes a fluid to a gas. So in both of these cases, the temperature remains constant during the phase change. So in the regions below the saturation dome, the heat flow rate is just the mass flow rate times HFG, which we can get from the property tables. So remembering back from thermodynamics 1 or 2, if you took the second part of it, here we have a graph of P versus V. P is pressure or temperature versus you can graph pressure or temperature. V is the specific volume. So here below the curve, this region here, you have a mixture, a saturated mixture. Part of it's going to be vapor, so part of it's going to be liquid. Remember, on this side, it's superheated. On this side, it's subcooled. So right at F, you have what's called a saturated liquid. So in a boiler, if you apply heat, the temperature stays constant until all the liquid turns to vapor, and you're at the saturated vapor point, the G point. And only then does the temperature rise. It's similar to a condenser, except you're going the other way. You're going from G to F. The rate of heat transfer in a heat exchanger can also be expressed in an analogous manner to Newton's law of cooling, as the flow rate, is equal to U times A times delta Tm. U is what's known as the overall heat transfer coefficient. A sub S is the heat transfer surface area, and delta Tm is the approximate mean temperature difference between the two fluids. So in the next sections, we're going to learn that the appropriate mean temperature to apply is called the log mean temperature difference, LMTD. So section 4 talks about the LMTD. So first of all, for a parallel flow heat exchanger, what you have is in the example, you have a hot fluid coming in, TH coming in, and the hot fluid coming out, TH. So the TH out is obviously going to be a little bit lower than the TH in. You have the cold fluid coming in, flowing across, obviously the hot fluid, cooling the pipe, and then the cold fluid gets heated up a little bit and comes out as TC out. So you have a delta T1 is the temperature difference between the TH in and TC in. Delta T2 is the temperature difference between the TH out and the TC out. So we define the delta T log mean is equal to delta T1 minus delta T2 divided by the natural log of delta T1 over delta T2. Now the book spends a lot of time deriving this formula, and it's you can look in the book for the derivation. It's not very exciting, but again, I'm just going to show you how to use this LMTD method using the definition. So an interesting note here. So here, for example, this is what's known as a counterflow heat exchanger. So you can see the difference here is that here you have the hot fluid still going from left to right, but the cold fluid is coming in and then traveling across the pipes from right to left. So they're traveling in opposite directions. An interesting fact is that the temperature difference between the counterflow is always greater than the temperature difference between the parallel flow. So just by changing the flow, the counterflow heat exchanger is always going to give a higher heat transfer rate than a parallel flow heat exchanger. So therefore, in the real world, in industry, you always see counterflow heat exchangers. The only time you'd ever possibly see a parallel flow heat exchanger was someone hooked it in backwards. And the reason for that fact is due to this right here. The counterflow temperature difference is always greater. So therefore, there would be no need to ever do a parallel flow. So the other two you can get type of heat exchangers we can talk about is what's called multiplast and crossflow. So in these examples, you have to use what's known as a correction factor. This derivation is not so simple, but the bottom line is you need to apply an F factor, which is the correction factor. Notice that also the delta T LM counterflow is the long mean temperature difference for the case of the counterflow heat exchanger. So here, we have what's called a crossflow. The hot liquid still comes in from left to right, but the cold fluid comes over and just flows across it. So this is a crossflow or a multiplast shell and tube heat exchanger. So I'll show you some examples of these when we get to the problems. But here you got the same kind of definition. Here's the delta TLM. We take the same delta T1, delta T2. This F value, okay, where do you get the F value at? Well, the F value comes out of a figure, out of a table, which I'll show you in the next couple of slides. So in order to get the correction factor, the F value, you have to know specifically what type you have. So for example, in type A here, we have a one shell pass and two or four tube passes, any multiple of two. Part B, we have a two shell pass and 4, 8, 12, any multiple of 4 tube passes. And so here shows you a little diagram of sort of what this looks like. This is a one shell two pass. Here's a two shell 4 pass. If you have C is a single pass cross flow with both fluids unmixed. So here's a picture of that. And D is a single pass cross flow with one fluid mixed and the other fluid unmixed. So you can sort of see what they look like by looking at the little figures. So these are defined in terms of what's called an R and a P value, as you can see. So we'll talk about what those are, but big T and small t represent the shell and tube side temperatures respectively. So T is the shell side tube, and small t is the tube side temperatures, which are shown in the figures here. So you can sort of tell what you're dealing with. So how you do this is you calculate the appropriate p-values by plugging in the temperatures, and you calculate the R value, and then you look on the curve to see where those match up, and you read off the correction factor uh, on the left-hand chart over here. So for example, if you calculated P and it turned out to be, let's say, 0.7, and then you calculated the R value and it turned out to be 0.6, then you would run over here and get a correction factor of 0.6. That would be 0.6 in that case. So one thing to note here too, so these are the same slides as figures as on the previous page, but to note the value of P goes from 0 to 1. It's a decimal between 0 and 1. On the other hand, the value of R ranges from 0 to infinity. So if you have condensation or boiling, R equals 0 for that case on the shell side, and R goes to infinity for a phase change on the tube side. So the correction factor is 1 for both of these limiting cases. So therefore, the correction factor of a condenser or a boiler is 1 regardless of the heat configuration of the heat exchanger. And you have to really tell that from well, in the real world, you're going to know whether you have a heat exchanger, or you have a boiler, or you have a condenser. In the problems, you're going to have to actually pay attention to the way the wording of the problem. So for example, let's take a look at example 11.3. Condensation of steam in a condenser. So steam in the condenser of a power plant is to be condensed at temperature of 30 degrees C with cooling water from a nearby lake, which enters the tubes of the condenser at 14 degrees C and leaves at 22 degrees C. The surface area of the tubes is 45 square meters, and the overall heat transfer coefficient is 2100 watts square meter Kelvin. Determine the mass flow rate of the cooling water needed and the rate of condensation in the steam of the condenser. So this is a condenser. So we're going to need the heat evaporation, the enthalpy, HFG, at 30 degrees. So we can look that up in table A9, and you can get it as 2131 kilojoules per kilogram. The specific heat of water at an average temperature of 18 degrees C is 4184 joules Kelvin, kilogram Kelvin. So again, what you can do here is he took an average between 22 and 14, which is 18, and use that for the specific heat. So here's our relevant formulas that we're going to apply. Q dot is UA times delta TLM. Of course, the delta TLM, we're going to apply that formula. We have we can solve M dot is for the cooling water is Q dot over CP delta T, and for the steam, remember this is a phase change, so it's Q dot over the HFG. So here's a good visualization. Here you have cooling water coming in at 14 degrees C and leaves at 22 degrees C. You have steam coming in at 30 degrees C and leaves at 30 degrees C. Now you may wonder, okay, well, why does it come in at 30 and go at 30? Because again, this is a phase change here. The temperature of the steam is not going to change. It's going to stay the same. So it's 30 degrees coming in, 30 degrees going out. Remember, it's that flat part of that curve on the from F to G. So here we can calculate delta T1, which is the temperature differences between delta TH minus T out cold, 8 degrees C. Delta T2 is TH out minus TC in, 16 degrees C. We can calculate the delta TLM, 11.5 degrees C. We can calculate Q dot. We know what U is, we know what the area is. We just calculated the delta TLM. So it's 1,087 kilowatts. So remember, that's also what the heat that given up by the water, right? The water gains that heat. the heat's transferred from the steam to the cooling water. So we can apply that for the cooling water. It's the same Q dot. We know what CP is, we know what delta T is. So the flow rate of cooling water has to be 32.5 kilograms per second. The flow rate of the steam is Q dot over the enthalpy, which is given here. So it's 0.45 kilograms per second. Let's look at example 11.4. So here we have a counterflow double pipe heat exchanger. It's to heat water from 20 degrees C to 80 degrees C at a rate of 1.2 kilograms per second. The heating is to be accomplished by geothermal water temperature available at 160 degrees C at a mass flow rate of 2 kilograms per second. The inner tube is thin-walled and has a diameter of 1.5 centimeters. If the overall heat transfer coefficient of the heat exchanger is 640 watts per square meter Kelvin, determine the length of the heat exchanger required to achieve the desired heating. So here we can look up the specific heats of water and the geothermal fluid. We can calculate Q dot. We know what M dot is, we know what CP is, we know what the temperature difference is in the water. 301 kilowatts. We can also plug that in. We can apply that for the geothermal water. We can solve this for T out. Basically, is what we've done. So with T out is Tn minus Q dot over M dot Cp. We can plug those values in. So the temperature coming out is 125 degrees C. So here's a schematic of it. You have the cold water coming in at 20 degrees C, going out at 80 degrees C. Those were given. You have the hot geothermal water coming in at 160 degrees C, and going out, and we just calculated what the out temperature is. It's 125 degrees C. So now we can continue. We can calculate this part up here. I just kind of carried forward from the previous slide. We can calculate the delta T1 and delta T2. So remember, this is hot minus cold, in minus out. Hot minus cold, this is out minus in. Especially these temperature differences minus those temperature differences, right, in the slide. So you get 160 minus 80, and you get the 125 minus 20. So the delta C, delta T, LM, you can calculate that. 91.9 degrees C. We can plug in the formula here. We know everything we need to know. Q dot is the same as 301 kilowatts. U is given, delta T, LM we calculated. The only thing we don't know is the area. So we can plug that in, calculate 5.12 square meters. So remember, if this is a pipe or a tube, the area is given by pi times the diameter times the length. So the length we can calculate, and we get 109 meters. Now think about this for a second. This is where your intuition has to come in. 109 meters. I mean, so obviously this is not very practical, right? So this kind of case, if you were a designer of heat exchange, you might say, well, look, we can't do this with a single pass. We're gonna have to have a double pass. We're gonna have to wrap this thing around, this cold water around in here a little bit. Maybe do a double pass or something like that, or a triple pass even. Whatever it needs to shorten this up. Very rarely in a factory you're gonna have that kind of length to work with. So let's look at another example. This is heating of glycerin in a multi-pass heat exchanger. A 2-shell pass and 4-tube pass heat exchanger is used to heat glycerin from 20 degrees C to 50 degrees C by hot water, which enters the thin-walled 2-centimeter diameter tubes at 80 degrees C and leaves at 40 degrees C. So this is down the figure down here. So it comes in at 80 degrees C, passes through the tube, and comes out at 40 degrees C. The total length of the tubes in the heat exchanger is 60 meters. The convection heat transfer coefficient is 25 watts meter squared Kelvin. On the glycerin side and 160 watts meter squared Kelvin on the water side. Determine the rate of heat transfer in the heat exchanger before any fouling and after fouling with a fouling factor of 0.00006 meter squared Kelvin watts. So here again, we can calculate the area, pi d times L. So it's 3.77 square meters. We have our Q dot is UA, and we got the fouling factor in here, times delta T. We can calculate delta T1 and delta T2 again. So remember how to do that. You got these guys minus those guys. 80 minus the 50. Then you've got the 40 minus the 20. You can calculate the delta T LM. Now once we calculated those values, since we have, we need to look at the P value and the R value here. So here we can calculate what P is. We get 0.67. We can calculate what R is. We get 0.75. Remember, these are just the temperatures over, the temperatures as defined there. So here, if you start out with a P value of 0.67, it's kind of hard on the graph here. You're somewhere over in here, and then you're 0.75, so you're somewhere over in here. So let's take a look at that again here. So 0.67 would be about here, and then 0.75 would be up about here somewhere. So you're about here. So if you come on over, I'd probably call it 0.9. He calls it 0.91. The key thing here is make sure you're using the right chart. So there's a 2 shell pass and 4, 8, or 12 tube passes. So you have to pay attention to the problem to know which of those particular 4 graphs to use. So let's take a look at the problem now that we have the information calculated. So in the case of no fouling, the overall heat transfer coefficient U is given by the following equation. You can calculate it to be 21.6. Then the rate of heat transfer simply becomes 1830 watts, since we know the U value, we know what area is, we know what the fouling factor is, we know the temperature difference. So if there's fouling on one of the surfaces, then we have to calculate with a new U value, which the only difference is you add this RF factor, the fouling factor. You calculate that as 21.3. So the Q value again looks the same. The only difference is U changes, 1805 watts. So it went down a little bit as a result of fouling as expected. So one more problem. So cooling water in an automotive radiator. So a test is conducted to determine the overall heat transfer coefficient in an automobile radiator. That is a compact cross-flow water-to-air heat exchanger with both fluids unmixed. So this schematic here shows it. You got the water flow coming in tubes. You got the airflow coming through, and they're separated by these plates. The radiator has 40 tubes of inner diameter 0.5 centimeters and length 65 centimeters. And the closely spaced fin matrix. Hot water enters the tubes at 90 degrees C at a rate of 0.6 kilograms per second and leaves at 65 degrees C. Air flows across the radiator through the inner fin spaces and is heated from 20 degrees C to 40 degrees C, shown here, 20 degrees C to 40 degrees C. Determine the overall heat transfer coefficient U of this radiator based on the inner surface area of the tubes. So the specific heat of water at an average temperature, so you take an average temperature from 90 degrees C to 65 degrees C, which turns out is 77.5 is 1.495. That's from table A9. So we can calculate what Q dot is, M dot CP delta T of the water, which we're given. The area is given, N is a number, we're told that N is 40 here, it's 40 tubes. Each tube has an area, so we can calculate that. So the total area of the tubes is 0.408 square meters. We can calculate delta T1 and delta T2 like before. So it's 90 minus 40 and 65 minus 20. So the delta T LM, 47.5 degrees C. Now we have to calculate the F factor. So notice here, you know, we're in graph D here because of the way the problem reads. So the p-value and r value you can calculate, and you can find the f value. So we can plug in the equation to find u. Q dot from the previous slide. A is given, F we know, the delta T LM we know. So we can calculate U is 3347 watts meter squared Kelvin.